Okay, so let's continue our investigation of determinants, and we're going to tie together some concepts with determinants, row reduction, elementary matrices, and actually we're going to bring in non-singular matrix like we usually do. So you'll see how this works out. So let's investigate some of these properties. First theorem mentioned here is that the determinant of the identity matrix is 1. Not really necessary to prove. We already showed that the determinant of an upper triangular matrix is the product of the diagonal entries, and certainly an identity matrix is upper triangular. It has 1s on the diagonal and 0s below. So next theorem is the determinant of elementary matrices. Remember that the elementary matrices were obtained from the identity matrix by elementary row operations. So the determinant of the elementary matrix for row swapping is -1. And the reason that is because we saw already that when you swap 2 rows of a matrix, you multiply the determinant by -1. So if you take the identity matrix, which has determinant 1, and then I swap 2 rows, the determinant is going to be -1. So that follows immediately. Second, if I multiply a row of the identity matrix by alpha, well, we know that multiplying the row of any matrix by alpha multiplies the determinant by alpha. And so if I have an identity matrix with 1, and then I replace one of the ones with alphas, if I take the product of these numbers, I'm going to get alpha, because I have all 1s except for a single alpha. Then the determinant of this matrix, if I add a multiple of one row to another, you can see that also directly. Remember that the matrix looks something like this. This is also an upper triangular matrix. Sometimes it might look like alpha down here, and that's a lower triangular matrix. The same argument applies. The determinant is going to be the product of the diagonal entries. Okay, so that gives us the determinant of elementary matrices. Right, now, this is a cool theorem. It says that the determinant of an elementary matrix times any matrix is equal to the determinant of the elementary matrix times the determinant of that matrix. Okay, this actually is called the homomorphism property. I'll write it here, homomorphism. Okay, which is a pretty cool property. You study that in abstract algebra. But what it says is if I multiply, again, if I multiply a matrix by an elementary matrix on the left, I can get the determinant of the result by multiplying the determinants. And this actually follows immediately from what we've just seen. That that if I swap 2 rows, of A, I'm going to multiply the determinant by -1. But on the other hand, the determinant of the elementary matrix that swaps 2 rows is -1. So that's going to give me -1 on both sides. If I multiply a row of a matrix by alpha, that's the same thing as multiplying by an elementary matrix. But the determinant of that elementary matrix is alpha, so that's the same thing as multiplying taking the matrix A and multiplying the determinant by alpha. And same thing for the other row operation. Okay, so this is kind of a cool theorem. And we'll use that for some theory properties in a little while. In fact, we're going to use that right away. We can show these 2 properties, which are very interesting. Singular matrices have 0 determinants. Okay, so we have another list of description. We have another description to add to our list of descriptions of singular matrices. Okay, now why is that true? We know that a singular matrix row reduces to a form of matrix that has some 0 rows. Okay, so if A is singular, A row reduces to a matrix with 0 rows. Now the determinant of this matrix with 0 rows is 0. On the other hand, if I can reduce A to this matrix by a series of row operations, that means I can write the matrix A as a product of elementary matrices times this matrix that has a 0 row. Okay, so that's the key issue here, that if A is singular, I can write it as a matrix with 0 rows multiplied in front by a series of elementary matrices. Okay? So how can I compute the determinant of A? Well, the determinant of A is the determinant of this product of matrices, but we know that the determinant of an elementary matrix times another matrix is the product of the determinants. So you can work that out like this. You can say the determinant of ES minus 1 dot 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 E1B is equal to, now this is ES times all this other stuff, so I can write that as the determinant of ES times the determinant of ES minus 1 dot 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 E1B. Now I can peel off another ES minus 1 because that's an elementary matrix times a bunch of matrices, so I just keep peeling them off, and my end result is this. And the determinant of A is the product of the determinant of elementary matrices times the determinant of B. But the determinant of B is 0. So it doesn't matter what these numbers are, the product is going to be 0. Determinant of A is 0, period. Okay, so A is singular. Now this, we have an if and only if. On the other hand, we can show that if the determinant, if A is non-singular, then it will reduce to a matrix that doesn't have 0 rows. Okay? And if it doesn't have 0 rows, here we have a number that's not 0. All these numbers are not 0. And we have the result that the determinant of A is not 0. Okay. In fact, if A is non-singular, then this matrix at the end is the identity matrix, which has determinant 1. Okay? So if A is singular, the determinant is 0. And on the other hand, if the determinant is if A is non-singular, the determinant is not 0. Okay, so here's just some examples. So here is just our long list of equivalent things. A is non-singular. We've now added another condition that A is non-singular if and only if the determinant of A is non-zero. Okay. Now, row reducing is the easiest way to determine determinant. Okay, and as I said, usually it's best to row reduce using the third type of row operation. Then you don't have to worry about multiplying the determinant by factors. Okay, so here's the final theorem, is that it's not just true, we showed already that the determinant of an elementary matrix times another matrix is the product of determinants. But in fact, we can replace this elementary matrix by any matrix and show that the determinant of the product of any two matrices is the product of the determinants. So I could replace this with a B here if I wanted to, and that'd be det B times det A. Okay. All right, so there's two cases to proving this. One is that A is singular. If A is singular, then we know that the determinant of A is 0, and we also know that AB is singular. Okay, so if A is singular, then the right-hand side is 0 and the left-hand side is 0. Okay, so no problem. Okay. If A is non-singular, then A can be written as a product of elementary matrices. Okay, since it can be written as a product of elementary matrices, I can replace A with this product of elementary matrices, and then I just peel them off one by one like I did before. The determinant of E1 times all this stuff, I can consider this as E1 times all this garbage. Then so I peel off the det E1, then I have the det E2 times this stuff. I can peel off the E2, and then peel off the E3, etc. It's an inductive process, and finally I get to det of B. Now, I know that the determinant of all these guys, I can put them back together now. And when I put them back together, I get this product times the determinant of B, and that's just the determinant of A. Okay, so this is kind of the final result, that very important result, that the determinant of a product is the product of the determinants. All right, so that finishes our study of determinants.